Chapter 9, Hypothesis Testing. This is the most used part of statistics in the real world. When you get out in the real world, what you see most, probably, what you care about most, maybe is this. Sampling's important, right? When we watch TV, we see lots of surveys said this, or this is, candidate this has this percent, and so we need to understand why that works or doesn't work, but statisticians probably use hypothesis testing more than anything else that they do. So hypothesis testing is really the first part of what we call inferential statistics, where we're trying to make decisions about things. So we're going to use the normal table, use the t table, use later on the f table and the chi-square table to either confirm or reject theories. Now, you have to understand what that means in statistics. We're going to use words like accept or reject, which don't really mean what accept and reject mean in the real world. So when we accept a theory, that doesn't mean it's right. That means the chance that it's right is high enough that we don't feel comfortable throwing it out. And we reject a theory not when we're absolutely sure it's false, but when the probability that it's false is so low, we just don't think it's likely enough to consider. So sometimes we accept theories that turn out to be wrong, and we reject theories that turn out to be right. In fact, some statisticians, in fact lots of statisticians, don't use the word accept. They use the phrase fail to reject. So we say that theory, if we think that theory has a good chance of being right, we just say we fail to reject that theory, which is our statistical way of saying could be right, but we don't want to say statistically, right? It's statistics. It's not proof. It's statistics. There's a chance. There's a probability. So we believe we know who's going to win an election, and we can fail to reject the idea that that person's going to win, but it doesn't mean we'd be surprised necessarily if they lost. So all we're doing in Chapter 8 is taking the confidence intervals we did in Chapter 9 and doing some math. So essentially, we're going to accept hypotheses that are inside the confidence interval and reject ones that aren't. And again, we're going to use 1% or 5%, 0.01, 0.05 as our alpha values, which is, again, the chance that we're making a mistake here. So here's the algebra. You don't really need to know this to do the algebra, but you need to understand what's going on. So we would always have aside from the sucky nature of Windows 10, we would always have the mean of the population equals the mean of the sample plus or minus this margin for error, right? So we do this, we ask people who they're going to vote for president, and they say, hey, I'm going to vote for Abraham Lincoln plus or minus, and we say Abraham Lincoln has 40% of the vote plus or minus 3%. And the formula for doing that, again, is that mu equals x bar plus or minus t times the standard error, t times s divided by the square root of n. What we want to do now is take this equation, and separate out the t all by itself. Okay? So the first thing we need to do is move the x bar over here. To do that, we subtract it. So we get mu minus x bar equals t times the standard error, t times s over the square root of n. Then we need to get rid of this part. To get rid of that part, we're going to divide, right? Divide by s over the square root of n. Okay, which makes that a 1 on this side, and then over here we get this. So we have this equation. Mu minus x bar divided by s over the square root of n equals t. And that's the equation we're going to use for confidence intervals. This could be a normal distribution, a z. It could be something else we'll talk about later, f's and chi-squares, and we're happy with all that. So we need to talk about what this really means. We go through a process. Again, do not think that this is some mean, nasty, difficult thing. Think that it's a recipe and you're cooking this. And you're going to put in, you start with, in one bowl you have 2 cups of flour and 1.5 cups of sugar and a little bit of salt and a little bit of baking powder. And in the other bowl you have half a pound of butter and 2 eggs and a teaspoon of vanilla, and you mix all that together, and then you mix those 2 things together and you throw the chocolate chips in, and pretty soon you have cookies. Okay? That's all this is. Even I can do it. All right? So we start by stating something called a null hypothesis. Null means no. Okay? And in this case it means no difference. So we have, let's say we're a drug company and we have an old drug and we have a new drug that we just invented. And we're testing to see whether the new drug works better than the old drug. We state our test as if there is no difference between the drugs. All right? We want to say no difference between the drugs. Or we try a new advertising campaign in our business compared to an old advertising campaign, and we want to test the hypothesis the new advertising campaign works better, but we don't actually test the hypothesis that the new one is better than the old one. We test the hypothesis that the new one and the old one are the same, no difference. Okay? Now we write this out this way. H is for hypothesis. That is the number 0. That's a 0. Why is it a 0? Well, it's a 0 because no difference equals 0. However, we don't say the word 0 because we're British. This was all invented by a British guy, and the British don't say 0, they say not. That's an N. We'll try that again. N-A-U-G H-T. So if you've ever read Harry Potter, when he gets his first broom, Ron tells him that his broom goes not to 60 in 4 seconds. It's a very fast broom. Not is the British way to say 0, which is what that is. So this is H naught. We say this as H naught, not H-O or H-0. It's H naught. And then we always say it in the population number. So it's mu. And in this case, let's just pick a number equal to 100. If we believe that we have an old advertising campaign and it brought in 100 people a day, and we think the new advertising campaign brings in 120 people a day, we're going to test that the new one is actually only producing the 100 people that the old one did. No difference. Okay, so we put in a number. Then we state what we call an alternative hypothesis, which is the opposite. And that is, in fact, HA. British don't say anything different. And we say that here mu is not equal to 100. You can also use a less than 100 or greater than 100 if you want to. So any one of those 3 works for the alternative hypothesis. Okay? And they all mean the same thing. One of these 2 hypotheses is going to be rejected, and one is going to be accepted. So we've got 2 hypotheses, one that mu is equal to 100, one that mu is not equal to 100, or greater than or less than 100, depending on the problem, how we want to set it up. And our point is that one of these we're going to accept and one of these we're going to reject. So step number 1, state the null hypothesis. Step number 2, state the alternative hypothesis. Step number 3 is then use the formula from the previous slide to calculate what we call a test statistic, which in our case is going to be a Z or a T. T if we're below 30 observations in our sample, and Z if we're 30 or above. Okay? So let's move on here now. Step 4 is we find something called a critical value. And interestingly enough, the critical values are in the t table. So every number in the t table is a critical value. And when we do a problem, we're going to go look for a number in the t table, and that number that we find in the t table is our critical value. And we'll do that here in a minute. Step number 5, we compare the two. We compare the test statistic and the critical value. And we're looking to see whether the test statistic is bigger than the critical value or whether the test statistic is smaller than the critical value. Those two comparisons, and we'll talk about which one we mean and which does what here in a second. So that's an S, by the way. I know that's hard to tell that's an S, but that's an S. And then step number 6, we draw a conclusion, and that conclusion is either reject or accept. And if you don't want to say accept, you say fail to reject. Right? So these two mean the same thing. You're going to do that to your one of these two to the null hypothesis, and you're going to do the other one of these two to the alternative. All right? So let's draw a picture. Here's a picture. Again, we have our normal distribution. We have our mean of the population. We just took a sample. Our question is, where is the sample mean? Is the sample mean here, or is the sample mean here? Okay? We're going to look our critical value up. Where does the critical value come from again? That's from the t table. And what the critical value does is cut our normal distribution into two parts. One part we call the rejection region, and obviously if something's out there we're going to reject it. And the other part we call the acceptance region, and if an answer is in there, we're going to accept it. So if our sample, if this is our mean, if this is mu, this is the population, so this is 100, okay? So we've been running an ad campaign getting 100 people a day, okay? That goes there. We have a new ad campaign that we think gives us more people than the 100 people we were getting before, okay? We have a critical value we're going to calculate, and that's going to be, maybe that ends up being 115. Okay? If our sample with the new technique turns out to be 112, it would be in here, and we would accept that our null hypothesis, which is that the new one isn't any better than the old one, that they're the same. Remember that. Our hypothesis is always that they're the same. All right? A lot of times in statistics, in fact, maybe most of the time in statistics, we do a test on purpose to reject our hypothesis. Not to accept it, we do it to reject it.